Hi everyone, I welcome you to this presentation that merely share my knowledge on the basic timer circuit using a 555 chip. This chip is widely used in a variety of applications such as clock source and a pulse generation. I turned the 555 chip into an Astable configuration to be a clock source in my future project, such as shift register, stopwatch, countdown timer, and many more. And we will begin shortly. And there you are. This is our 555 chip looks like. We have the pin out. Pin 1 is ground. Pin 2 is trigger, pin 3 is output, pin 4 is reset, pin 5 is control, pin 6 is threshold, pin 7 is discharge, and pin 8 is the VCC or the power supply. And I will show you the 555 chip, this very small chip. And it looks like this. Okay, it's just a very small chip. And now next is on how the basic clock source is made. And of course, the 555 chip will not be functional without the external components, and that is why I made this design for you to be able to at least understand on how the chip will work. First is we have the resistor 1 and we have the resistor 2 and the capacitor. This is the power source, and we have the output, and we have this ground. With this chip, I used this project as a clock source of my counter. If you are constructing a countdown or count up or shift register or any other projects that involve clock source, well, 555 chip is very important. And here is it. This is the complete drawing with external components and its values. See? R1 is 2 kilo ohms, R2 is 2 kilo ohms, C1 is 200 microfarad. Since I don't have a 200 microfarad capacitor, what I did is I connect two capacitors in parallel that will equate to 200 microfarad. And pin 8 is our power source. Here I have a 4.7 volts DC power source, and I have this output. The output can be measured across pin 3 and ground. You can check the output using a multimeter. You will connect the output here, the positive probe and the negative probe to the ground. So in order for you to appreciate the output, you can connect an LED with a protection resistor to prevent your LED from damage. Before constructing with this project, you have to calculate the output time. The output of this pin tree is the clock pulse. Okay, and later on I will show you the formula on how to calculate the clock pulse. There is a time high and there is a time low and there is a duty cycle, and of course there is a frequency. Here we are. This is the formula. First is the formula of the time high. This is the one. Time high is equal to normal logarithm or ln times 2 times r1 plus r2 times c1. By the way, this ln is not a logarithm log. If you will calculate it in your calculator, you have to press ln, then open parenthesis 2, then close parenthesis. That is how you calculate the ln or normal logarithm. The resistor must be expressed in ohms and the capacitor must be expressed in farads. Next is I'm going to substitute the value. T high is equal to normal logarithm times 2 times the total of two resistors, 2000 ohms plus 2000 ohms. As you remember before, I show you the value of the external components, and I will repeat. As you can see here, see, R1 is 2 kilo ohms or 2000 ohms. R2 is also a 2000 ohms, and C1 is 200 microfarad. This is according to my design. Now we will continue. Normal logarithm times 2 times 4000. 4000 is the total of the two resistors, R1 plus R2, times 0.000200. This is the 200 microfarad. Do not write here 200, otherwise you will end up a wrong calculation. Normal logarithm times 2 times 0.8. 0.8 is the product of 4000 times 0.000200. And here is it. This is our answer for the time high, 550 milliseconds. Next, we will proceed to the calculation of time low. Of course, if there is a time high, there should also be a time low. The formula for time low is normal logarithm times 2 times the product of R2 and C1. Now I'm going to substitute the value. Normal logarithm times 2 times R2. R2 is 2000 ohms times C1, which is 200 microfarad or 0.0000200 farad. Please take note, as I mentioned here in this, that resistor must be expressed in ohms and the capacitor must be expressed in farad. Okay, please take note. And here is it. Normal logarithm times 2 times 0.4. 0.4 is the product of 2000 ohms and the 200 microfarad. And the time law is 0.28 seconds or 280 milliseconds. Since you have calculated the time high and the time low, of course, you need the calculation also for the total time duration of a clock. The total time is the time high plus time low. Time high is 550 milliseconds or 0.550 seconds plus time low, which is 0.280 seconds. And finally, we got the total time, which is 0.830 seconds or 830 milliseconds. Since you have the total time now, we can proceed to the calculation of the frequency. As you know that a clock source must have a frequency. If you have the time and also you have the frequency, and by the calculation of the frequency, you need the time. Now I will show you. Frequency must be expressed in hertz. Okay, so this is the formula of frequency: 1 over time total. We will substitute the value. Frequency is equal to 1 over time high plus time low. So since we have calculated this one, we can make a shortcut. This one, according to here, right? 550 milliseconds plus 280 milliseconds is equal to 830 milliseconds. So this is it. Now, next step. Frequency is equal to 1 divided by 830 milliseconds. Then the result is like that. So our frequency of the clock is 1.2 Hertz. Later I will show to you the accuracy of this frequency, the accuracy of the time, the accuracy of the time low, and the accuracy of the time high. I will show to you through the oscilloscope. Okay, so since we have completed the theoretical explanation according to this circuit, now I will show to you to the actual connections, and this is it. Okay, so according to the output, this is our output. I connect or install an LED across the pin tray and the ground. So this is the one. Okay, it's a blinking. Blinking means there is a clock source, a clock output, sorry. When the LED is on, it means the time is high. When LED is off, it means the time is low. So therefore, the activity of this LED indicates the clock output of your circuit design. Time high, time low, time high, time low, time high, time low. Okay. And as you notice, time high takes a little bit longer than the time low. Okay, as you can see, and this is our R1, resistor 1, and our resistor 2, and capacitor 1. As you notice, take a look to the capacitor. There are two capacitors, right? Because each capacitor has a value of 100 microfarad. When you connect two capacitors in parallel, it will add up its value. So 100 plus 100 becomes 200 microfarad. This configuration is according to the schematic diagram. Okay, so please don't be confused. You can copy this one and you can make a test in your home or in your shop, especially for those who are beginners. I hope it will be useful to you. Okay. Now go back to the calculation. The lead indicator is the evidence if my calculation is correct or not. As you can see, time high is 550 milliseconds and time low is only 280 milliseconds. Therefore, time high takes longer than the time low. As you can see, just observe. See? According to the book, the output waveform of this clock is in square wave. This is the one, huh? This is the output waveform of the clock. This upper line from here to this point, that is the time high. Okay, and at this lower line or the bottom of the square wave is the time low. From this point to this point, that is the duration of time low. And take a look to my calculation with this. Time high is 550 milliseconds. So from here to here, that is 550 milliseconds. And from this point to this point, which is the time low, that is 280 milliseconds. Okay, and if you will add up the time high and the time low, the result is 830 milliseconds. This one. Okay, I just go back to this calculation in order for you to understand well. 830 milliseconds. So in one cycle is from this point. Take note. One cycle of a square wave is from this point to this point. Okay, start here, going this one, and go down, going this one. That is the complete cycle. Okay. So if you will add this one, time high plus time low. Therefore, the total time from this point, one cycle, to this point is 830 milliseconds. So this is it. I wrote the figure so that you can get exactly what I am explaining. So time high 550 milliseconds plus this one time low is 280 milliseconds. The total time duration for one cycle is 830 milliseconds. Now, to prove that this is correct, I will use an oscilloscope to show you the actual waveform. Now I will connect this positive probe, this one, to the output of the clock, this one, and I will connect this negative probe to negative terminal. That is it. Okay, so just a review. I put the positive probe here and the negative here. This is the one. And now this is the actual waveform. Let's take a look for the waveform. So we have the time high and the time low. Okay, from this point to this point, that is a one cycle. Okay, and I will show you if my calculation is correct or not. I will show you the time or the period. In my calculation, the result is 830 milliseconds. That is according to the theoretical calculation. Now I will bring you to the actual result. See here, this is the period, that is 812 milliseconds. Okay, and about the frequency, my calculation for the frequency is 1.2 Hertz. This is based on the theoretical calculation. Now I will bring you to the actual result. See? So now at least you have an idea on how the clock source is being investigated through the use of oscilloscope. And here also the waveform of the voltage across the capacitor 1. As you can see, that is a sawtooth waveform, not a square wave. So this point on top means the charging. As you know in the book, that capacitor is charging, discharging, charging, discharging. Okay, so charging, discharging, charging, discharging. That is the work of the capacitor, and I will show you this in the actual through oscilloscope. By the way, to get this waveform, I will connect another probe across the capacitor. And now this is my second probe, this one, no? Okay, this is my channel 2. I will connect this probe to the positive of capacitor here. Sorry, it's very difficult to do the connection. Okay, and I will put this to the negative terminal, so I can install over here the negative terminal, or I can make an extension because it's not easy. So I can make this extension, this pin, so I will connect it here. So this is the negative. Okay, now I will show you to the oscilloscope on how it responds. There you are. Okay, so look at our channel. This is channel 1 for the clock output. Channel 2 is for the capacitor charging and discharge activity. Okay, and based on the book, it goes like this, and we investigated this one to make it clarified. See, this point is the charge, this point is the discharge, charge, discharge. This is the waveform of the voltage across the capacitor C1. I have to proceed to the duty cycle. By the way, duty cycle is the ratio of the time high to the total time times 100%. So here is it. The duty cycle is expressed in percent. The formula is time high divided by time high plus time low. Time high plus time low is the total time, right? So we have calculated this one before already. Here is it. 550 milliseconds divided by total time. And here is it. 550 milliseconds divided by 830 milliseconds times 100%. And 0.6626 times 100%. This is step by step, okay? So here is it. The duty cycle of our clock system is 66.26%. Now I will compare this theoretical calculation to the actual result in oscilloscope. And here is it. So look at my duty cycle. And that is all about. I wish you like my presentation, and see you in the future's upload. Thank you very much.